Good afternoon. My name is Joan Johnson-Freese, and it is my pleasure to chair this fifth panel on institutional arrangements in solar system exploration. We have four papers to be presented by four astute individuals who will consider relevant issues based on their experience and their research. All their bios are available to you, so I won't take the time to go through them. I will just briefly mention, we have Jim Burke from JPL, the legendary Jim Burke. It's been my pleasure to work with him for years with the International Space University. John Sarkissian, an operations scientist at CSIRO, which I looked up, and it's Commonwealth Scientific and Industrial Research Organization from Australia. Michael Neufeld, museum curator in the Space History Division at the National Air and Space Museum, and Petar Markovski, a PhD candidate in History of Science at the University of Oklahoma. The issues they will be considering are several. Institutional management, for example, will be considered, as will institutional focus. How management issues, arrangements, and focus can affect the ability to execute a highly sophisticated science and engineering program. And we've already been hearing about that this morning through different international collaboration examples. And these papers will consider and go into depth on those issues, including international collaboration, the complexity and the potential that is added by expanding missions beyond national, or extending missions beyond national borders. And clearly the complexity expansion is across the board, not just with the science and engineering considerations, but with the political and legal. One point that has really fascinated me over the years as an observer and analyst of these institutional arrangements is the role, and perhaps changing role, of the program manager. I'll give fair warning now to the panelists that that'll be a question I will be raising to them, and I hope you, the audience, will be noting your questions that they can address as well. We'll follow the same format as we have already, 20-minute presentations, 5 minutes of Q&A, and then the panel will assemble at the end. So with that, I would like to introduce Jim Burke to talk about the foundations of solar system exploration at JPL, how the first mariners and rangers built them.
Thank you, Joan. I'd like to begin by giving you a little background on the co-author and my successor as Ranger Project Manager, Bud Schirmeyer. Many of you, of course, know him from his distinguished later reputation at JPL as project manager of various projects, Mariner 6 and 7, and the Voyagers, as of when they were launched. He was one of the first of a long succession of excellent project managers on Voyager. But what I'd like to do here is take a couple minutes to tell you a little bit about the earlier part of his life. He and I graduated from Caltech after meeting each other as freshmen 70 years ago. 70. And while we were at Caltech, we, of course, enjoyed all the Southern California recreations: soaring, sailing, skiing, surfing, whatever else there is that doesn't begin with S. He brought me down off the mountain with a broken leg twice. So we know each other pretty well. And in any case, it was my very good fortune to have him in position as manager of JPL Systems Division, which is where all the subsystems get to try to work with each other. That's what he was doing while I was being the first project manager of Ranger. But our experience at JPL went way back from there. We both were hired in 1949. So that by the time Ranger came along, we both had been working at JPL for more than 10 years. And one part of what I'm going to tell you from here on is how there was a collision between us and everybody else involved in the project, all the way up to Congress later in the game. Because we really thought we knew what we were doing. We were experienced, both of us were experienced project managers under the Army, and we knew how to do what we were doing. Ranger presented us with a more complicated and bigger project to do, but not one that was different in any essential way from the things we'd been doing before. Therefore, there was a definite collision between us and our leaders once we were transferred out of the Army and into NASA. Because NASA had a whole lot of engineers who were just as experienced and just as smart as us, and it took us a while to realize that they were our bosses. Well, that's a little bit the theme of this presentation, okay? Oh, I don't have a script. Well, no, I can't read it up there. I'll have to read it here. Sorry about that. JPL, of course, launched the first Earth satellites, Explorer 1, 4, 5. But quickly it was determined that Earth satellites were going to be a big business in a crowded field, and we as a university laboratory shouldn't really be in that field. So we chose to go beyond low Earth orbit, first target being Mars for the 1960 the 1960 launch window, which was the first time in human history that something could be launched to Mars. So that was the objective initially. Retreated back from that, driven by circumstances, to the moon. That was the process as of 1958. Okay, the von Braun team, very experienced, of course. We had to go through quite a transition with them because they ended up in a very anomalous position. Once NASA was formed, the von Braun people were NASA's agent for procuring launch services from the Air Force. If you can find a more difficult situation for somebody, that's where they were. And it's to their great credit that individuals in both the Air Force and the Army saw to it that in spite of all the institutional rivalries and other things that were happening at the time, they managed to pull it off. They got us our launch vehicles. Tremendous confusion, not just about launch vehicles, but really about everything as to who was going to do what. But rather quickly, in 1958 and 59, we discovered that we just couldn't do that Mars launch window. It was way beyond anything we could logically hope to meet. So the big Mariner, called Mariner A, that was planned for that mission, was abandoned, and was decided to build a Mariner for Venus in 1962, a couple of them, that would be derived from the smaller Ranger lunar spacecraft that we were building. Ranger already had solar panels and a high gain antenna, because those are features that you have to have for interplanetary missions. You don't need them for the moon. But we had them on Ranger because we visualized it as a precursor to planetary missions. 3-axis attitude control, pointing an antenna, getting solar power, and being able to execute a mid-course maneuver, trajectory correction. Those were the features that had to be on the Mariner, so they were on the Ranger. And the Mariner became to be called Mariner R, derived from Ranger, okay? Mariner A became Mariner R. Okay, the Air Force and our Huntsville friends got us the Atlas Agena, the Deep Space Net and Space Flight Operations Facility, necessary for both lunar and planetary missions, began building at that time. Common bus variable payloads. Everything you see on this slide was an attempt by us to try to meet the requirement of building reliability through successive operations and still meeting the difficult demands of planetary missions where you can't change the schedule unless you're prepared to slip it for years, as in fact did happen with Curiosity, the big rover. Okay. Science on every flight. I had what now seems a very peculiar attitude about science. I insisted that every flight carry scientific instruments for two reasons. One, we didn't know which flight or flights might succeed. Two, engineering development of science instruments in flight is as important as that of any other subsystem on the spacecraft. And I simply thought it's up to the project manager to figure out, after receiving advice from scientists and comparing that with what you can do, what you can accommodate, then I'll tell the scientists which of them get to come and which other ones have to wait for another launch. Can you imagine a viewpoint more different from that of, first, science is the objective of the mission. Come on, guys. Two, there's a whole structure out there of scientific advisory committees, NASA, and this and that. Project manager simply has to sit and watch all of that happen and then deal with the result. Well, that wasn't the way I started. October 1960, I was appointed project manager. On the 10th of October, big rocket takes off. It was the classic old original one, except the upper stages weighed more than 30 tons. And we watched the very slow acceleration of that and thought, oh my goodness, what is this thing? Then on the second one, on the 14th of October, our telemetry was good enough to show that it had four big boosters going off like that. So that was when we first began to understand what the Molniya configuration of the Soviet launch vehicle looked like. When President Kennedy was inaugurated, he gave a talk that was very largely about the contest between American values and the subversive and threatening emanations that were coming out of the USSR. On the 4th and 12th of February, as you heard this morning, they got two launches off, and the second one sent Venera 1 on its way. Then Yuri Gagarin, Kennedy announced Apollo. If you can imagine a more propulsive environment than the one we were in to get Ranger 1 and 2 going, we had a lot of pressure on us, much of it provided by ourselves. We really wanted to get going, and we did. Things moved fast. I skipped over a whole lot of trouble. Originally, when NASA when we and the Germans were transferred into NASA, we already had a plan for upper stages on the Atlas, but they were not the right ones. The Air Force Agena was the right upper stage to use, but it took, oops, how did that happen? I'll go back. I went back too far, sorry, okay. Huh. What happened? Okay, never mind. Something about the launch vehicles was on the slide that is now missing. Oh, okay, all right. Marshall was placed in a very tough position, but we did end up, again because of the dedication of individuals in the agencies who put our needs above the interagency disputes that were all going on then. We got the launch vehicles that we needed. I told you about how we didn't really like being jerked around by people who were our essential colleagues professionally and suddenly turned out to be from NASA, a new agency that we'd never heard of, and they were in charge. Our lunar scientists were the leaders in the profession. Geochemistry, gamma ray spectrometer, geophysics, seismometer, and geomorphology, the television. Those were the instruments on the Lunar Rangers, and the scientists in charge of those did not give us any trouble. They really did a tremendous job, and they are famous for it. They were already famous in their own professions, of course. We had a problem with non-lunar scientists, space physics, and I'll get to that a little later. Okay, and we had a sort of a philosophical problem with not the lunar scientists. They were fine, they were on board, they followed our schedule. Ranger 1 and 2 were planned as test flights, not aimed at the moon, but to have a high enough apogee that they would take the spacecraft out to where it could acquire the sun and earth references. And since it was going to do that out in the magnetosphere, it might as well have some space physics instruments on board. It had an excellent payload designed by the prominent space physicists of the day, plus an ultraviolet telescope looking back at the Earth's hydrogen corona. 3, 4, and 5, I told you about their instruments, and on Ranger 6 to 9, the objective was reduced to just television. Well, here's the example of the bus with one of the several different payloads. The bus is hexagonal because of a vanished upper stage configuration. So it was adapted to the Agena. The tower on the top has the space physics instruments, and at the very top, the omnidirectional antenna. So that was the configuration of Rangers 1 and 2. Ranger 1 and 2, because of Agena upper stage troubles, never got to their high apogee orbits. They were stranded in low Earth orbit. The spacecraft appeared to be okay as far as you could tell in that orbit. Ranger 3, we had a spacecraft that was fine. It was injected. The Atlas had a guidance error, but the Ranger acquired the sun and Earth and began to do what it should do. But then when the mid-course maneuver happened, one vector was pointed the wrong way. There had been a double sign inversion between the spacecraft and the ground equipment, so it missed the moon. Ranger 4, something got across a couple of pins between the Agena. When the spacecraft came away from the Agena, something shorted out the Ranger. If it had had the female side of the separation connector, that probably wouldn't have happened. On Ranger 5, I'll show you a picture of that one. But Ranger 6, this is after I had been replaced as project manager by Bud Schermeyer, and I'll tell you more about that later, but here's this brief version of the story. When the Atlas staged its first stage engines off, a plasma cloud enveloped the vehicle and shorted out the television. Fascinating. This is the configuration of the lunar ones with the seismometer ball at the top and the gamma ray spectrometer out on a boom and the television looking down. I seem to keep skipping over slides. Well, okay. This is the power switching and logic unit in Ranger 5, proof test model of it. Shows you something about our packaging. People look at JPL's packaging and they say, hey, those look like locomotive parts. Well, we found out they have to look like locomotive parts if you don't want to amplify vibrations from the launch vehicle, etc. And that's why our packages look the way they do. A backside of this little item, you see the arrow pointing there, that screw got warm and that did us in. We had a good spacecraft. Again, it had acquired the sun and earth, was on its way to the moon this time. Atlas Agena was okay, fine. But then we went to the Ranger 6, 7, 8, and 9 configuration with just television and a crash into the moon. Okay, that's what I'm here to tell you. Robotic deep space exploration demands extreme attention to risk, and even then, you don't always succeed. Technical risks, all the ones in the Ranger, both in the launch vehicles and the spacecraft. The failures were at interfaces. Management risks, I guess I don't need to go too much into that. But after Ranger 5, the project capsized and Schirmeyer replaced me. Then he had the failure of Ranger 6, which took it all the way up to Congress. Enormous trouble. And everything was focused on the RCA camera payload, while in fact, the failure happened during the Atlas booster staging back during ascent. So, big, long failure investigation entirely focused on the place where the failure didn't occur. And we may never have known about the cause of that failure had not a solar physicist among us continued to persist in looking into it and investigating all the records. And he finally decided he had a convincing story, and he took it, not to the project manager, but to his division manager, who thought about it and said, that's interesting. But it was quite a while before everybody became convinced that that was the actual cause of the failure. When a plasma cloud went up the sides of the Atlas and back down, for just less than a second, it was enough to turn on the TVs and burn them out. Thank you. I put a couple of my references in here. I sort of stretched the point a little bit. Thank you, Joan.
You're right on time, so go ahead and take 5 minutes. No, go ahead and take questions.
Okay. Yeah, okay, since I'm going to ask myself one question, why did you put this in about yes, reference 4, 1966, declassified 94. The beautiful book by Wes Huntress and Mikhail Marov tells the real story about all of the Soviet missions. What this reference is my story about what we thought they were doing, published in the Studies in Intelligence, and wasn't declassified for a number of years.
During your days out at JPL, I was at ABMA. I was with the Army Ballistic Missile Agency back in those 50s years. And you guys were transferred in October 58. We held out with the Army until July 1960. The Army didn't want to lose the von Braun team. And it was finally Eisenhower who personally intervened. And so we transferred officially on the 1st of July, 1960. Also, we developed the Jupiter IRBM. But then you got the Air Force. We were told that the Army was not going to deploy that missile, that it was going to be deployed by the Air Force. So we had to paint out U.S. Army, put U.S. Air Force in there. Redstone Arsenal filled with Air Force personnel learning how to operate the Jupiter IRBM, which was deployed Turkey. But that Jupiter put in your upper stages. You remember the Juno 2?
Oh, yes, of course.
You didn't talk about that. Could you say a few words about Juno 2?
I said the launch vehicle picture was a little bit confused. That was a strong understatement, and you've just heard a little more about some of the various pieces of spaghetti that were all squirming around there. Go ahead.
Jim, can you just talk a little bit about how you and everybody realized the seriousness of the reliability issues? What did you expect going in? Did you think you could just get away with, seeing if it worked, and if it didn't work, you'd fix it? But then, was there a moment when you all realized that you were in a much more unforgiving game?
I think the answer, the best simple, quick answer, short answer to that question is, yes, reliability was dominant in our minds, and we tried to test everything you can test. And you get to a point where you've tested something so many times that you've worn it out, and it's better to leave it alone. But, as I said, these failures happened with extremely subtle causes, none of which would have been revealed in a ground test. For example, on Ranger 2, the gyros in the Agena were not turning when it took off. Why? Because the blockhouse instrumentation was designed in such a way, no matter how much you test it, you can't tell whether the gyros are turning or not. Okay? Well, that was corrected, but we'd already lost one mission, so fine. The next Agena, the gyros were indeed turning, but we didn't have 50 missions the way you do in the Army. Okay?
Jim, in one of your slides, and concluding one, I guess, it was said that the politicians' invention of policy do not help, but probably worsen the situation, I completely agree with you because I just experienced it in my own career, But was it just the case in the Ranger program when the policy tried to assist you somehow, but actually interfere badly?
How did the politicians?
The politicians were faced with a problem that's very difficult for a politician. To us, it looked as if they were wasting their time and ours, but in their world, they really did have to consider whether we, happy engineers who were just going along, always thinking we could make the next one work, and eventually we did make the next 3 of them work. Fine, everybody ended up a hero. So from an engineering standpoint, we did exactly the same thing we'd always previously done in the Army. You find a failure, you fix it, launch the next thing, it has a different failure, you fix that, and eventually you get to where you want to be. Okay, but Ranger was operating in a different environment. And the answer to Mikhail's question is, politicians could have done us tremendous damage because one question that arose, and it was treated in the aeronautical press then, is what's a university laboratory doing in this business anyway with a $60 million mission, 500 people working on it, big deal, So that question, had it gone the other way, had NASA not told the politicians to, hey, get off our backs, the JPL knows what it's doing, leave us alone.
Okay, thank you very much. We're going to have more time for questions at the end. Our next presenter is John Sarkissian, who's going to talk about Mariner 2 and the CSIRO Parkes Radio Telescope.
Wrong John. Which one was that? Okay. Well, firstly, I'd first like to thank Bill Barry and the organisers for inviting me along here to address you this afternoon, and it really is a great honour, so thank you very much for that. The CSIRO Parkes Radio Telescope is one of the world's great research instruments. It is arguably the finest single-dish radio telescope in the world. In fact, in 2006, a study published in the journal Nature ranked it second only to the VLA in terms of its scientific impact. It is owned and operated by the Commonwealth Scientific and Industrial Research Organisation, or CSIRO, of Australia. And when it was built in 1961, it was the most advanced radio telescope in the world. It was also recognised very early on that its design made it a near ideal instrument for tracking spacecraft in deep space. This attracted the attention of NASA JPL, where it had its most profound impact in the design of the large aperture antennas of the deep space network. As you can see from this table, the space missions that the Parkes telescope has been involved in spans the 5 decades of the solar system exploration, from Mariner 2 at the very beginning all the way through to the latest mission, Curiosity, just a few months ago. The highlight was undoubtedly the Apollo missions, from especially Apollos 11 through to 17. We also played a critical role in the Galileo mission to Jupiter, and also in the Huygens landing on Titan, where we actually were able to salvage the Doppler wind experiment through our observations. But how did it all begin? Well, it was conceived by Edward Taffy Bowen in 1954. Taffy was the visionary and dynamic chief of the CSIRO's radiophysics division for 25 years, from 1946 to 1971. Under his leadership, the radiophysics division developed as a pioneer and world leader in the emerging science of radio astronomy in the immediate post-war years. But by the early 1950s, Taffy was thinking of the next stage of development of radio astronomy in Australia, and he determined that the best all-round instrument for continuing the CSIRO's pioneering efforts in radio astronomy was a large, fully steerable dish antenna. At the time, such an instrument was beyond the budget of the CSIRO, so he called on his old boy network, so to speak, of contacts that he'd built up during the war to seek the necessary funding. Firstly, he approached the Carnegie Corporation. At the time, it was the president of the Carnegie Institute in Washington was headed by, the president of it was Vannevar Bush, who during the war was President Roosevelt's science advisor, the man who initiated the Manhattan Project, and he was also the founder of the National Science Foundation. And from his very close personal relationships, professional relationship with Vannevar Bush, he acquired $250,000 to get the project started. He then followed up with a similar amount from the Rockefeller Foundation. The president of the Rockefeller Foundation was Dean Rusk, the future Secretary of State in the Kennedy and Johnson administrations. Again, he knew Taffy during the war period. And Richard Casey, who was the man who actually set up the radiophysics laboratory within the CSIRO as a secret wartime laboratory, was a minister in the then Australian government and responsible for the CSIRO, and he managed to convince, and he was a great supporter of Taffy and of the telescope project, and he managed to convince the Australian Prime Minister to support it with matching funds. And then combined with additional private donations and with the additional funds from the Australian government and the Rockefeller Foundation to make up a shortfall towards the end of the project, he was able to acquire just over $1.4 million to build the telescope, which even in those days was considered ridiculously cheap. The telescope itself was designed by the Freeman Fox and Partners, a British firm. They were actually famous, especially in Australia, as being the designers of the Sydney Harbour Bridge. And They were contracted to design the telescope to CSIRO specifications, and the CSIRO engineer, Harry Minette, supervised the design of the telescope and its drive system from 1956 to 1959. This was much longer than they expected, but it paid off in the end because it meant that they got the design right. The telescope actually incorporated several very innovative design features. I'll just come to that in a moment. Firstly, it was pivoted in the centre. It's like an inverted umbrella, as you can see. It had an out-azimuth mount, which is unusual for its time for a structure that large. Also, in order for it to track objects smoothly across the sky, it incorporated a new invention of the master equatorial system. And it was basically just a small equatorially mounted optical telescope located at the intersection of the altitude and azimuth axes of the telescope. Essentially, the dish was slaved to that equatorially mounted optical telescope via a servo drive system that enabled it to very smoothly track objects across the sky. And finally, it had spiral purlins on the dish to give it strength. The site chosen for the telescope was near the town of Parkes, about 350 kilometres west of Sydney in the central west of New South Wales in Australia. And the reason it was chosen was because of those mountains in the background of the photograph there. They protected us from the radio emissions from the larger population centres further east, such as Sydney, for example. And so the area was a very radio quiet site, which was essential for a large sensitive instrument like Parkes. That young fellow there, standing next to the stake where the actual telescope was built, he's now 59 years old and he's a good friend of mine. He's the local farmer still. The main constructor for the telescope was MAN of West Germany. And so already you can see that it's beginning to take on the of an international project with the United States, Australia, the British and the Germans all involved in the construction. The construction itself began in late 1959, and over the next 21 months, when the Germans arrived to build the turret, they were able to weld the ribs into shape, and then they lifted them one at a time, bolted them onto the turret, and then when that was done, they then put the focus cabin up on the apex, and then panelled the dish. And as I said, it was all done in the amazingly short period of just 21 months. And that was and there was very little problems encountered in the construction, and it was mainly due to the time spent in designing it initially. The first tip of the telescope occurred in October 1961, and then mid-October 61, and then 2 weeks later it was officially opened by the Governor-General of Australia, Lord Delisle. The first director of the observatory was John Bolton. He was a legendary figure, a pioneer of radio astronomy in Australia, and he also, in 1955, moved to Caltech and started the radio astronomy program there, and founded the Owens Valley Observatory, which is which we had very close contacts with over the years. But how did we get involved in the space missions? Well, the story goes back to the period, the interest that JPL had in Parkes went to before even when the telescope was built. Began on the 6th of March 1959 when the US Army's Pioneer 4 spacecraft flew by the moon at what was then a record distance of 650,000 kilometres, and unfortunately NASA JPL could not communicate with it effectively, even though it was a perfectly functioning spacecraft, because its small 26-metre antenna at Goldstone just didn't have the sensitivity to communicate with it effectively. And so JPL realised that what it needed was a much larger and more sensitive antenna than the 26-metre antennas that it was planning for its deep space network, or the fledgling deep space network. And so the requirements for such an antenna were that it needed to be 6 to 12 dB improvement over the existing 26-metre array they were planning, which meant that it had to be somewhere in the order of 60 to 80 metres in diameter. It had to have optimum performance at 2.2 gigahertz, at S-band. In other words, the surface had to be extremely accurate. It needed to have a pointing accuracy of about 1.2 minutes of arc. And finally, it needed to have a slew rate of around 10 degrees a minute. And it was no surprise at all that these requirements matched the proposed Parkes telescope very, very closely. Consequently, during the tender and construction phase of the telescope, JPL made several representations to the CSIRO with the view of formally incorporating it into the Deep Space Network. Finally, however, a cooperative space exploration program was proposed, and you can see that it was for the occasional use of Parkes for data acquisition of a short-term nature where an extremely strong and reliable signal was required. And in fact, to this day, it is still the basis and rationale for Parkes' inclusion in space tracking operations. In 1962, a NASA research grant was awarded to the CSIRO to study the dish characteristics with a view to it contributing toward the design of the proposed JPL large aperture antennas. William Pickering, the JPL director, invited the CSIRO to participate in the feasibility studies and specification reviews of the JPL antennas. The grant also called for a detailed study to determine the performance parameters of the Parkes telescope in regards to those parameters you see there, the structural behaviour, characteristics of the drive system, radio frequency performance, vibration characteristics, but also measurements of the dish shape in the zenith and tilted positions. As a result of these studies, over the next few years, more than 30 research papers were published on the design and performance of the telescope. Parkes was not only the most advanced radio telescope in the world, it also became the most extensively studied. And the reason for it is because this information was considered to be of critical importance in the design and construction of the JPL antennas. The Caltech and JPL luminaries involved in that design were people such as Bruce Rule, Bill Merrick, Eb Recton, and so on, and they liaised very closely with the CSIRO engineers, Harry Minette and others, to ensure that the DSN antennas were operated as well as they'd hoped. Now, another aspect of the Parkes telescope impact on space tracking was in the location of the DSN stations. As you can see, the very first station was located at Goldstone, it was only just a few hours drive from JPL, but that then dictated where the other two stations would go. They needed to have their stations roughly equidistant around the globe, 120 degrees apart roughly, and so in the late 50s, early 60s, the other two stations were located at Johannesburg in South Africa, and also at Island Lagoon at the Woomera Rocket Range in South Australia. But for various reasons, which I won't go into, just lack of time, they had to shift the locations of those other stations, and one went to Madrid and the other went to the Tidbinbilla Nature Reserve, very close to Canberra, the Australian capital. And the reason Tidbinbilla was chosen was because Taffy Bowen was the chairman of the site selection committee, and he chose that site because Tidbinbilla was on almost exactly the same longitude as the Parkes telescope, because he argued that being on the same longitude, the two would see the same sky simultaneously, and that in the future NASA may want to link or array the dishes together to enhance the capabilities so that the two working together would be a much more powerful, more useful instrument than the two working individually. And of course that was realised some 20 or so years later with the Voyager 2 encounters of Uranus and Neptune, and also very critically with the Galileo mission to Jupiter. Now, it was during this design and study period that Mariner 2 was launched. As you all know, it flew by Venus on the 14th of December 1962, and it flew within just under 35,000 kilometres of the surface. Now, Taffy Bowen and Harry Minette decided that tracking Mariner 2 would be an excellent demonstration of the Parkes telescope's capabilities for communication at great distances. And essentially the experiment would be a simple one involving the measurement of spacecraft position, signal level and Doppler frequency. It did not include the reception of telemetry, but was simply intended to establish the technique and measure the performance of a 64-metre antenna. Parkes tracked it for 2 weeks, beginning on the 20th of December 1962 until the 3rd of January, when the signal was finally lost. JPL loaned Parkes an L-band transportable phase-lock receiver, which the astronomers dubbed the Ancient Mariner, as you can see, because it looked quite old even then, I think. But the thing that I found most amazing was that it had a 20 hertz gate that could be manually tuned. So the astronomers had to know the frequency very, very precisely and tune it to very close to the Doppler shifted frequency in the passband, and so they could get it in that 20 hertz gate and then lock onto the signal. Because these tracks were on an informal basis, JPL did not provide position and frequency predicts. So Harry Minette resorted to calculating these himself, using slide rule and pencil and paper. But he needed to know both the position and the frequency to lock onto the signal. He experienced great trouble at this, as you could imagine, because he was never sure whether the position was right and the frequency was wrong, or vice versa, or both. So eventually, after a week of fruitless effort, he contacted JPL, who sent him the predicts, and he immediately was able to lock on to the signal, as you see there. And here I found in the National Archives his hand-drawn plot of the results, and we just zoom in a little bit there. You can see that the Parkes telescope had an overall 5 dB advantage over the 26 metre antennas, in this case the one at Woomera, and it should have actually had an 8 dB advantage, but because a circularly polarised feed was unavailable, the astronomers had used a linearly polarised astronomy feed instead that incurred a 3 dB penalty. Nonetheless, the experiment was considered a great success, and the results were included in the study reports that verified the soundness of the design. And as a consequence of these, Parkes became the model for the JPL large aperture antennas. As you can see, they were all pivoted in the centre, just like Parkes. They had an out-azimuth mount, they incorporated the master equatorial system, and they were all 64 metres in diameter. The Goldstone dish was eventually commissioned in May 1966, but before then, Mariner 4 was flying by Mars, and the Goldstone dish was still a year away from completion, so Parkes was approached to provide the 64 metre capability for the DSN. 22 images were returned of the Martian surface, and Parkes provided a 3 dB improvement of the existing DSN array. In fact, all antennas combined, Parkes provided double the strength of that. The data from Parkes was combined with those from the other stations and used to produce improved images of the Martian surface, and you've all seen this one, the famous image 11, which made astronomers very, very disappointed because they were expecting to see verdant forests. Instead they had a desolate lunar landscape. Now, perhaps the most famous mission Parkes was involved in was Apollo 11. No history of Parkes could be complete without a mention of its role. It began in October 1968 when John Bolton was visiting Caltech. He was invited to dinner at the home of Bob Leeton, a friend and colleague of John's, and one of the PIs for the Mariner 4 mission. Also at the dinner was Eb Recton, the head of the Goldstone project, and during the course of the dinner, John was asked if he could make available the Parkes telescope for the upcoming Apollo 11 mission, but in particular for those few short hours when the lunar module was on the lunar surface. And because human lives were at risk, both he and Taffy Bowen agreed. And as is well known now, 600 million people, 1/6 of mankind at the time, witnessed the Apollo 11 moonwalk live on TV through pictures received at Parkes. The story is far too long for me to go into detail in this short presentation, but I invite you to check the Parkes website and also the Honeysuckle Creek website for more details on that. And I think, oh yeah, it's just that there. And the beginning of the broadcast, NASA were just, TV's the thing that everyone remembers nowadays, but at the beginning of the broadcast, NASA Houston was switching between the signals being received at Goldstone and Honeysuckle Creek. When they finally switched to Parkes, it was so much better they stayed with Parkes for the remainder of the 2.5-hour moonwalk. And just to give you an idea of why they did that, on the right, no, sorry, the left, you have an image of Armstrong descending the ladder, sourced from Goldstone. 20 minutes later, when they were using the Parkes feed, you can see Aldrin coming down the ladder. You can see the improvement in the picture. Honeysuckle Creek had a very good image also, but because of its smaller size and lower signal-to-noise ratio, had a grainier image. The equivalent picture 20 minutes later, when Aldrin was about to step on the lunar surface, was from Parkes, and again you can see the improvement and understand why it was involved. Over the years, we've had a mutually beneficial partnership, the CSIRO and NASA. Whenever Parkes has supported a NASA space mission, we've gotten a better radio telescope out of it as a result. And in return, NASA has a more capable antenna for the next mission that they approach us for. You can see all the surface upgrades and the focus cabin and so on were all funded by NASA over the years, and we've got a much better telescope, and NASA has a more capable antenna for its next mission also. So in conclusion, I'd like to finish with a quote by the US Ambassador to Australia in 2003 when he was at Parkes to launch the Mars tracks. Tom Schieffer, and basically he said, to quote, "The Parkes telescope is like a trusted friend, always there when we need a hand. The relationship between CSIRO and NASA is very much like that between the United States and Australia. A friend that's as friends that share common values and dreams." And I have a picture there of the ambassador and the officer in charge of the Parkes telescope, John Reynolds, playing a spot of cricket on the dish during the opening. The ambassador had to learn how to hold the cricket bat correctly. He thought it was a baseball bat at the time, but it worked. And just to finish up, just 30 seconds, there is an epilogue to the story. On the 27th of August 1962, Mariner 2, the first interplanetary spacecraft, was launched to Venus. That just happened to be the day that I was born. Okay. And when New Horizons arrives at Pluto in July 2015, we could say, in all honesty, that in the space of a single human lifetime, the entire solar system would have been explored. And I think that's pretty impressive, and Parkes was there from the very beginning, so thank you.
I'm sure there are lots of questions, but we have time for just one right now.
Oh, we had a softball for it.
But my serious question is, I had not realized before actually that Parkes was, if you will, a prototype of these large steerable antennas. And what amazes me is that you got it right the first time in terms of critical things like the loading on the figure of the telescope. Was there some special innovation that enabled that, or was it just real attention to details and specifications?
It was essentially just the attention to detail, but also I didn't have time to go into great detail, but one of the engineers that provided the really innovative ideas on how it should be done was Barnes Wallis, a famous British engineer. He was famous during World War II as the inventor of the bouncing bombs. And it was his idea, essentially, to have an Altaz-mounted telescope with the master equatorial. He invented that concept. And also the spiral purlins. He actually developed that idea for the R-100 airship and the Wellington bombers. And that's what gave the dish that strength. And it's also the reason why we've been able to upgrade the surface continually over the years, because that it did have that strength, and the designers of the JPL antennas were extremely interested in that, and they took a lot of those design features, as you saw, and incorporated it. With the added, they have to be able to transmit as well as receive, so they had a Cassegrain feed rather than prime focus as we do. But it really did come down to the designers designing it properly at the beginning, which is why they took their time and then built it quickly. It's a good case of hastening slowly, where take your time, design it, and then do it quickly at the end. And of course, they were the same people that designed the Sydney Harbour Bridge, and that's still up and still will be for a century or two more, I hope. So,
Thank you.
Thank you.